Okay, great. Well, thanks all for joining us. DeWitt Sumners is here to tell us about the helicity of Seifert framed defects. So, go ahead.
Thanks, Alan. It's a real pleasure to be here. I'd like to thank the organizers for inviting me. But in particular, I'd like to say happy birthday to Luke Kaufman. He's been a very good friend of mine for years, since the old days in knot theory. A story about Lou is that we were together supported by the program in mathematics and molecular biology. So this was a national center for the applications of mathematics to molecular biology. And the founding director was the late Nick Cosarelli at UC Berkeley. He was a molecular biologist. And this center had mathematicians, biologists, chemists, physicists, computer scientists, statisticians from around the United States. Some other members of PMMB, as it was known, were Jim White and Vaughn Jones. And if you listen to Sophia Lambropoulos' talk earlier today, she has shared a picture of herself and Lou defending a poster at the 2002 PMMB meeting in Santa Fe. So I'm going to be talking about applied topology. So questions that many topologists has is, why is topology so useful in science? And the reason is because topology is discretized geometry. And any change in topology is a big change, and it can often be experimentally observed. So knot theory explores the codimension 2 complexity of 3-space and of higher dimensional spaces, but 3-space is the one we're interested in today. And so knot theory, as it turns out, is very useful in physics, in chemistry, and in biology. So the next picture is a picture of knotted plasmid DNA. It's an electron micrograph. So this was taken in the Cosarelli lab in about 1985. And it was, in fact, this electron micrograph, this picture of knotted DNA, that got me very interested in applications of knot theory in biology. It turns out that what this knotted DNA is telling you about the enzyme that made it. So the enzymes are proteins that attach themselves to DNA. And in this case, they break DNA apart. They open it up and pass DNA through itself by means of an enzyme-bridged transient break in the DNA. Other DNA enzymes can do site-specific recombination, where they insert DNA into plasmids and into chromosomal DNA. So the idea to use topology is, this is topological enzymology. The idea is to see if you can use topology to write equations that'll tell you how the enzyme was binding to the DNA, how it wraps the DNA around itself, and what it does specifically when it breaks it apart and reconnects it. So topology is useful in writing down equations and solving them. I will not be talking about this today, but I am going to be talking about this, fluid dynamics. For many years, people were trying to blow knotted smoke rings. It's very difficult to do with a cigar. You can blow unknotted ones, but it turns out that Bill Irvine at the University of Chicago was able in 2013 to produce knotted vortex tubes in the water. So what he did was, as you can see here, he developed hydrofoils. You print them on your computer. You coat the hydrofoil. Here's an unknotted hydrofoil, and here's a trefoil knotted hydrofoil. You coat them with bubbles, and then you pull them down quickly, and out comes out as a vortex tube, and the bubbles go to the middle of the tube and can be visualized with laser sheets. So you can see the time evolution of these vortex tubes. The unknotted one sort of just keeps going to the right here. Nothing much happens. But this knotted one, this trefoil knotted one, twists itself up and reconnects, as you'll see in the video from the Irvine lab. I'm sorry. Somehow my video got lost. So we're going to focus on vortex tubes and fluid dynamics and flux tubes and magnetic fields. And helicity is a lower bound for the energy of the configuration, and it's determined by linking numbers. So that's what helicity is. It's determined by linking numbers of these tubes. And the framing of each vortex tube is determined, if it's the Seifert framing, by the Seifert surface, which co-bounds all the center curves of the vortex tubes. So what is a defect? Well, it turns out that the center lines of the vortex tubes are the defect. They're a defect in a phase map. You take the complement of the link in 3 space and map it to the phase circle, and it's defined everywhere except on the link itself. So you can think of a defect in terms of, suppose you're at, say, a football game, and you're standing in the middle of the football field on the 50-yard line, and the field is full of people as well as the stands. If the wave were to begin, it would be going around the stadium. So at any instant in time, you'd see all the people that are at exactly the same phase. There are the people doing the wave, and it goes all the way around. But if you're standing in the middle of the field, the people all around you are doing the wave. No matter how you decide to wave yourself, it's going to be discontinuous. So in that case, the defect is where you are in the middle of this phase map. So the phase is continuous, well-defined everywhere except at the defects. So here's the album of fluid motion, which shows you some reconnection events. And here's reconnection events. They happen on the sun with magnetic tube lines. So the tube starts here on the sun, and it consists of magnetic field lines. You have a reconnection event, and it spits out a solar flare. So here's a cartoon of a reconnection event. Well, you have 2 of these vortex tubes with center lines. Here's the first center line, the blue one. Here's the red center line. And then they do an anti-parallel reconnection. So the directions are going, the right-hand screw rule is telling you the direction of these vortices. And you have a reconnection event. And here you see the reconnection event happening. And here's another, if you've got, say, a flux tube, you have these magnetic field lines oriented oppositely. Here you can see the rotation in one direction here, and in the other direction here, anti-parallel orientation on the center lines. And here are 2 of the field lines reconnecting. So I want to study what happens to the topology and the geometry of vortex tubes under reconnection. A reconnection preserves the curve orientation, as you've seen, but it changes the topology drastically. One circle becomes 2 circles, and if you reconnect them, it goes back to 1 circle, and so on. So iterated reconnection on circles gives you a circle, 2 circles, and so on. So here again is the Kleckner picture, and finally here is the picture of the vortex tube. So here's the Hopf link coming off of those tubes, and you're going to see a reconnection event here in a minute. So it's rotating around to show you that it is the Hopf link, and those are the center lines of the vortex tubes. And it has a reconnection event right there. And now you have a single circle. It's unknotted, and it's going to undergo reconnection one more time. So right here. There it is. The reconnection happens. And now you have 2 unknotted, unlinked circles. So that's the cascade that Renzo Rica mentioned in his talk. If you start with a trefoil, the trefoil moves around, and then it juxtaposes 2 oppositely oriented edges, and you have a reconnection event right here. Here's a close-up of it. And after this reconnection event, it converts the trefoil to the Hopf link. This is now the Hopf link. And then the Hopf link reconnects to a single circle, which then reconnects to 2 unknotted, unlinked circles. So that's the complete cascade of the trefoil vortex. So here's a picture of the vortices and what happens. You start with a trefoil. It has a reconnection event, anti-parallel. That produces the Hopf link. And the Hopf link has a reconnection event that produces another large, unlinked, unknotted circle. That one has a reconnection event, and that produces 2 unknotted and unlinked circles. And so this reconnection cascade happens both in fluid dynamics and in molecular biology. There's a sequence of events where the idea is to produce 2 unknotted, unlinked DNA circles, and it goes through this same cascade. So here's sort of a close-up of the reconnection event itself. You can see the vortex lines, they start to wind around each other, and then they reconnect. And if you put sign crossings on this projection, the number of sign crossings doesn't change. But that doesn't tell you that the writhe is invariant. That's something that I'll prove. So this is the sign convention for oriented skew lines in space. This is how you compute linking numbers from a diagram. I'm going to talk about the writhe. So here I'm thinking of, say, a circle that's sitting in 3 space. Think of it as rigid, and I take a projection, I compute the sign crossing number. I rotate it around, take another projection, and I compute the sign crossing number. Then I average all those projections. So you average over all the projections, so that's points on a unit 2 sphere. So you average the projected writhe over the space of all projections, which is the unit 2 sphere in R3. And here I've got some DNA pictures. Here's DNA of very low writhe. Here's some DNA of increasing writhe. And as you increase the writhe, this is high writhe, and this is low writhe for these DNA mini circles. I'm going to compute the writhe in terms of a piecewise linear picture. So suppose I've got 2 edges in a piecewise linear circle, E1 and EI and EJ. And WEI-EJ is the signed area on the unit 2 sphere covered by the direction vectors pointing from one oriented edge to the other. So it's all the projections in which you can see these oriented edges cross themselves. And so you get open sets on that unit 2 sphere, and you add up the area, and that's this WEI-EJ. So you can compute the writhe this way. Suppose you've got an oriented polygon with edges A1 to AN. The writhe is you divide by the area of the unit 2 sphere. You add up all these writhes, you have AI versus AJ for all I and J. And that gives you the writhe of an oriented polygon. You can compute the linking number by edges the same way. Suppose you've got 2 disjoint oriented polygons, A1 through AN, that's A. B is B1 through BN. The linking number of AB, you simply can look at AI against BJ for all I and J, add them all up, and that gives you the linking number, which is a topological invariant. The writhe isn't. It's an invariant of geometry, but it's related to the linking numbers I'll say in a minute. Suppose now I've got the disjoint union of 2 oriented polygons, A and B. A has in edges, B has im edges. I want to compute the writhe of A union B. So I've got the edges of A versus the edges of A, plus the edges of A against the edges of B, plus edges of B against the edges of A, plus the edges of B against the edges of B. So this is the writhe of A, this is the linking number, this is the linking number, and this is the writhe of B here. So this verifies that the writhe of the disjoint union is the writhe of A plus 2 times the linking number is symmetric in the 3 sphere, plus the writhe of B. And now when I'm doing reconnection, I want to think of it as follows. I've got a red curve A, a black curve B. I'm thinking of them now as rigid, and at the edge, this red edge and sort of aligns with this black edge here. And I'm going to translate B and make those 2 edges coincident to give me an intermediate theta curve. So if I translate B and make the edges incident, I get the theta curve, A connects some B star. If I remove the interior of this common edge, I get the reconnection, or the connected sum as it's called. So I'm going to compute the writhe of this picture. So the writhe of A union B, as I said before, is writhe of A plus 2 times the linking number plus the writhe of B. And translation preserves all 3 of these quantities. And I'm thinking about, for the writhe of the theta curve here, the intermediate theta curve, I'm counting the common edge twice, once up and once down. So here's sort of a picture showing this common edge. The AN is coincident with BM, and they're oriented oppositely, and I'm counting them twice. But if I count them both twice, the edges are oriented oppositely, so the writhe contribution of AN cancels out the writhe contribution of BM, and so I can forget it. So that means that the writhe of A union B is in fact equal to the writhe of the connected sum. And this means that the writhe as a function is a continuous function of time. As you take your curves and move them around in space, that's by diffeomorphism. And then when you do a reconnection event, the writhe doesn't change discontinuously. The topology does, but the writhe does not. So a single curve, if you're reconnecting a single curve, it approaches the theta curve, and the value of the theta curve intermediate is the limiting value is the writhe of the reconnected pair of curves. So here I want to talk about, say, a flux tube. Here I've got a center line C gamma. This is the tube gamma. I've got say, a flux curve here, a magnetic curve, a magnetic field line that's on the boundary of the tube. And together, these you can think of this as C gamma, the center line, and you can think of this as C prime gamma, the push off. And you have this ribbon that connects up the center line with the outside curve. And giving this picture here with the ribbon and the push off, you can define the incremental twist of the ribbon. So you have the tangent vector here, and you've got a vector that goes from the point on the curve to a point on the push off, and the cross product here is shown. And the incremental twist rate is you look at how this collection of vectors twists as you go along the curve here. And you do this line integral, and you get a real number, and this is the writhe of the curve. And it turns out that the linking number is a famous theorem of Calogeriano and White, that the linking number of the center line and the push off here is the linking number is the twist plus the writhe. So this topological invariant is the sum of two geometric invariants. They change as the thing moves around, but the linking number stays the same. So if you've got a solenoidal vector field, I'll tell you what the helicity is. So if B is the solenoidal vector field and A is the vector potential, Bx, the vector field is compact support in domain D, and it's confined to knotted and linked tubes in D. So these are the vortex tubes or the flux tubes. And the kinetic helicity is you simply integrate A dot B dV over the domain D. It's a measure of twisting, knotting, and linking of field lines. And the absolute value to this is a lower bound to the energy of B. So that's why people are interested in helicity. But fortunately for us topologists, Moffat and Rika have a solution to what is the topological meaning of this. If you have gamma, a flux tube with center line C gamma and flux ribbons R gamma, the flux ribbon has boundary C gamma union C gamma prime, the center line and this push off. The helicity, according to Moffat and Rika, is the flux phi squared times the self-linking number of gamma, which is the writhe plus the twist, as I said before, the Calogeriano-White theorem. And it's a topological invariant. So the self-linking number, so that is the helicity of a single flux tube. So we're going to reconnect, say, two tubes of the same flux, so we'll assume that phi is equal to 1 for this calculation. So suppose I have two flux tubes with the same flux, phi equal to 1. The helicity of the union of the two flux tubes is the self-linking number of one plus the self-linking number of the other plus 2 times the linking number. I'll rewrite this as the writhe plus the twist of the first flux tube alpha plus the rise plus the twist of the second flux tube alpha using the Calogeriano-White theorem plus 2 times the linking number. That can be rewritten like this: the writhe of one plus the writhe of other plus 2 times the linking number. Now that's a quantity we looked at before. It's the writhe of the two center lines plus the twist. So you can call this first one, this one here, the writhe helicity. This second one, the twist helicity. And what I've proved is that the writhe helicity is conserved. So if you forget the twist of the ribbon, the writhe helicity is what is conserved when you do a reconnection event. The twist, and as Sheeler and Irvine have pointed out, that in water, the twist helicity is dissipated by viscosity, and the writhe helicity persists. So it's the writhe that's sort of important in this turbulence cascade. So I'll now talk about the Gross-Pitievsky isosurface. So the Gross-Pitievsky differential equation is the one that's commonly used to study vortex dynamics. It tells you about the motion of the vortices, and you can model the reconnection events by means of this PDE. So I've got a vortex link in R3, and I have X as the link complement. It's R3 minus the link. I'll get a phase map on X. This is where the phase map is defined on the complement. So it's a map from X to S1. And if you take star, the base point in S1, the pullback of the base point under the phase map is the Seifert surface. It pulls back a surface plus a normal direction on the surface from the circle itself. So it's kind of a oriented surface, and the boundary of this oriented surface is equal to the link L. And it turns out that X has a Seifert surface if and only if the complement admits a phase map. So I showed you that if you have a phase map, you've got a Seifert surface. On the other hand, if you've got a Seifert surface, how do you get a phase map? Well, the Seifert surface itself has a disk bundle, a line bundle. It's regular neighbor. It's a line bundle, and it's trivial. It's V cross the interval. And if you think of the interval as going from minus pi to pi, you simply take the complement of the interval and map it to a point, pi on the unit circle. So that gives you a map. It sort of takes the bundle and stretches it out and makes it go around the circle. So here's a picture due to Renzo Rican, Simone Zucker that shows you the time evolution of one of these Seifert surfaces as it undergoes reconnection. So here you see it moving. This is the Hopf link, and you're going to see a reconnection event in just a minute. And I believe the reconnection event happens sort of over here. So it happens kind of right here. There's the reconnection event. And you're going to, so now you have a single circle and a site and a disk bounding it. And you're going to see another reconnection event here where two circles are now produced. And then it does it again to give you three circles, I believe. So if L is an oriented link, then a Seifert surface for L is an oriented surface such as the boundary of V is equal to L. And so in examples of Seifert surface are this GPE, Gross-Pitievsky equation, isosurface from the phase map. Optical knots have Seifert surfaces. The Belousov-Zhabotinsky reaction in chemistry has a reaction wavefront, and that is itself a Seifert surface that's moving around in space, rotating around the boundary, which is some sort of knot, a defect knot in the wave itself. And for the Seifert surface, I'm assuming that the ribbon and the push-off live on V. So you have the Seifert surface V, it comes into the tube neighborhood, it intersects, its boundary is the middle of the tube neighborhood, the middle curve itself, and the intersection of the Seifert surface with the tube neighborhood is that ribbon. And so the ribbon and the push-off is the boundary of the ribbon that lives on the boundary of the tube. So here I have a picture of the center line K. It's a trefoil knot. The Seifert surface is in blue here. And the intersection of the tube neighborhood of V with is K prime. This is the push-off that lives on both the Seifert surface and the tube around K. So if K prime, the black curve, is the push-off of K on V, and the intersection of V with the tube around K is K prime. And if you let V prime be the trimmed Seifert surface, you simply trim off the interior of these ribbons. So it's V minus the ribbon around K. So the boundary of V is K, the boundary of V prime is K prime, and K does not intersect the trimmed Seifert surface. It turns out that linking numbers are determined by intersection numbers. So this is Seifert's work, I guess. So if B here, the curve B is the boundary of a cycle V2, a two-cycle V2, a surface you can think of. And the curve A cuts through it here and intersects it in a point with this kind of orientation. The linking number of AB is in fact the intersection number of A with V2. It's +1 in this picture. So I'm going to prove that Seifert framed links have zero helicity. So if I have a flux tube with center line C gamma and flux ribbon R gamma and flux phi, this is the flux ribbon boundary of these two curves. The flux ribbon lies on a Seifert surface V. The helicity, in this case, of a single curve, since the self-linking number is zero, I've got the zero framing, it's the Seifert framing. So its linking number is zero, so the helicity for a Seifert framed single curve is zero. But the same sort of proof works for a collection of curves. So suppose I've got a Seifert framed link L. So L is the union of a bunch of center lines AI as I goes from 1 to n. I've got the Seifert surface V whose boundary is equal to L. And V intersects the boundaries of tubes around each AI, producing ribbons and push-offs. AI prime is the push-off, and Ri would be the ribbon Ri on all of these things live on V, the Seifert surface. I delete the interiors of the ribbon to obtain V prime. So it's the trimmed Seifert surface, which is living sort of in the bounded complement of the link. The boundary of V prime is the union of all these push-offs. Now, L certainly does not intersect V prime. It's living on the interior of all these tubes, and V prime lives completely outside of these tubes. It intersects the boundaries of the tubes. So the intersection of L with V prime is the empty set. The linking number of AI and AJ is equal to the linking number of AI with the push-off, because you can move AJ to AJ prime. It's the push-off inside the Jth tube. Just move across the ribbon. So you can isotop AJ to AJ prime, leaving AI fixed. So that proves that the linking numbers are equal here. And for that reason, it's equal to the linking number of the two push-offs. This is for I different from J. And for the self-linking number, AI, you have the linking number AI with its own push-off. If I take Li prime to be the push-off of AI union all the other AJs, so I different from J, the linking number of AI with Li prime is equal to the intersection number of AI with V prime. So that gives you the self-linking number of AI plus the summation of all the other linking numbers, AI with AJ for I different from J. And this is equal to zero because this linking number is the intersection is the empty set. So you get zero for every I here. And it turns out that this is a necessary and sufficient conditions for the existence of a Seifert surface. This proves that it's necessary. In a minute, I'll prove that it's sufficient. That if you've got this information on the tubes themselves, this kind of framing, that you can build yourself a phase map where you've got a Seifert surface that does all this. And I'm going to call this number here the self-linking number of AI plus the summation of the linking AI AJ for I different from J. I'll call this the individual helicity of AI. And the total helicity of the link is the sum of each of the individual helicities. So the total helicity of a link is the sum of these individual helicities, and each individual helicity is zero, therefore the sum is zero. So this proved that a Seifert framed link has zero helicity. So there's a theorem. The theorem I'm claiming is that if you've got the Seifert framing, you have the Seifert framing if and only if this individual helicity is zero for each I. So that's a necessary condition. How can it be sufficient as well? Well, it turns out that the framing gives you a map of the boundary of the tube to the phase circle. And the interesting part here is that this push-off here corresponds to the linking number of the push-off with the center line. So the self-linking number is the linking number of this red push-off with the black center. And the framings of this tubular neighborhood are one-to-one correspondence with linking numbers. And it's these linking numbers. So the phase map is defined because you already have the framing. The framing gives you the phase map. So you've got a phase map already defined on the boundary of X, the bounded boundary, the boundary of the bounded link complement. It's a bunch of tori. So you have phi defined on boundary X to S1. You have, this is the inclusion map. You want to extend this to a map on the entire complement X. Once you've done this, you've got the phase map everywhere. You can simply then use the pullback to get yourself a Seifert surface. Well, this is the standard setup for obstruction theory. So here you've got the set of homotopy classes of maps of boundary X to S1. S1's a K pi 1. And that's in one-to-one correspondence with the one-dimensional cohomology of boundary X, coefficients in Z. Poincare duality takes you finally down to homology, where this map here goes down to an n-tuple here, and the n-tuple is simply all these push-offs, A1 prime, A2 prime, and so on. You've got all the push-offs here. You take that vector of push-offs and you map it over to the homology of X. And what happens is that each of the push-offs goes to the linking number with all the other curves. So you simply get the ith component of this image here of the map. I'm trying to get my, here. You take the map, the n-tuple of push-offs here goes to an n-tuple, and each entry of the n-tuple is the individual helicity of the ith component of the link, and that's 0. So the thing you started with here goes here, and it goes to 0 here, so it's in the kernel. By exactness, you have something back here that goes to this. You then pull it up here, and you have yourself a map. And so now you're done. You now have a map that matches up with this one. And anti-parallel reconnection preserves the Seifert surface. So here's a picture. You saw that in the illustration from Rika and Zucker that I showed you, the green Seifert surface for the Hopf-link. So anti-parallel reconnection preserves the Seifert surface, so the Seifert framing gets preserved. So helicity is writhe plus twist, and it's 0, so that means that if you've got Seifert framing, the writhe is equal to minus the twist. The Seifert framing is preserved under anti-parallel reconnection, so the helicity is 0 just before and just after reconnection. Since it's 0, you have writhe equals minus the twist. And since you have writhe helicity conserved by antiparallel reconnection, this also means that twist helicity is conserved by antiparallel reconnection for Seifert framed situations. So I may be a little early here, but I'd like to thank you for listening. And these are the co-conspirators here in this project. So thank you, and I'll take any questions you've got.